Okay, hello everyone. Welcome to day 3 of the winter school, and it's great to see all of you all once again for the morning talk. Today we have Carlos Zapata-Carratalá speaking to us, and Carlos has been working with us for a long time. In fact, he initially started off as a mathematical physicist from the University of Edinburgh. Then later on, Carlos has been developing his own works, both in terms of community engagement as well as research. He's the president and founder of the Society for Interdisciplinary Research. Correct me if I've not stated that right, and feel free to advertise your society when you start. So you're welcome to do that. Later on, Carlos has been one of the main initiators and founders of the Higher Rarity project. He's been really very interested in meta-mathematics, higher rarity mathematics, and related things at a scientific level. And at Wolfram, he has been working on several projects at the Institute, coordinating scientific activities, working on some of these new algebras. With Nick, Carlos has also built this hypergraph backlet, about which today you'll hear a bit, and both Nick and you and Carlos will be guiding you how to use it. It's an amazing new tool for new mathematical discoveries. So it's great to have you. The stage is all yours.
Well, thank you very much, and hello everyone. It's a real pleasure to be addressing you all, and I hope that everyone gets something useful out of today's session. I will be introducing some of the basic ideas in my research, and specifically what I've done with the Wolfram Institute. So thanks for the very lovely introduction, Cersei, very comprehensive. I am indeed, aside from working at the Wolfram Institute, I am the president and director of the Society for Multidisciplinary and Fundamental Research, SCMF. So I'm going to drop the link in the chat just in case some of you want to check it out. I'll just copy it now. It is a nonprofit organization that operates internationally, and we organize sort of multidisciplinary events. Stephen has been in several of them. Some of the people here actually have participated in the past in some of our community gatherings and so on. So yeah, I welcome you to have a look at that. If you, there's a little link to join the Discord and to be up to date with messaging. So if you are curious and would like to participate, just click on that. Everything is free and open. And all right, so yes, I am here to...
Before you get started, could you just improve your audio a bit? Because sometimes it's as if, there's it slightly goes up and down.
Yeah, I'm gonna connect with the phone again. I am not in my usual office environment, and the audio in this laptop is not the best. So let me just quickly do that. Because if you're gonna listen to me for about an hour, so I want you to have at least a reasonably pleasant experience. Let's see. All right. Can you hear me?
Much better, yeah.
Yeah. Okay. So, right. Let me then start with the presentation. Here we go. So, as I said, I'm going to be introducing some of the very basic concepts of my work. If there are any questions or any clarifications that you think will be useful, please stop me. Otherwise, I'll just proceed. This will be fairly elementary. There's not going to be any, sophisticated mathematics or anything like that. So it is very much encouraged to, interrupt me and ask questions, because that's what we're here for. So we title this Hypergraph Calculus and Hypermatrices. So I hope to give you some basic understanding of these kinds of objects, hypergraphs and hypermatrices, and how they are related to algebra and concepts that you are probably familiar with. So before I get started on that, let me give you some motivations. As I'm sure you're now familiar with, we are coming from the Wolfram Physics project, where hypergraphs have been used as the kind of structures that allow for generative systems, and that seemingly, or in some cases, they model geometry, they model space-time, and so on. So the basic objects, as you can see here, are this so-called hypergraphs, which essentially amount to collections of multiple relations of discrete elements, also called nodes, and those relations are also called edges or hyperedges. So here is a summary of what you see in the physics project. You go to the website, you can see some information. So you have some kind of small initial state over here. You apply this computational rule. We'll get into the details later how this works. And then after a long process, you know that it's not a single string of actions, but it's actually kind of a multi-threaded process. You get eventually one single state down here, and that looks like this. So you begin with something very small like this over here, and you end up with something like that. So that's one part of the motivation. There is hypergraphs and hypergraph rewrite systems that have been used in the Wolfram Physics project, and obviously elsewhere, but chiefly there that we want to understand. And then there's also the metamathematics project, where you're trying to understand the emergent mathematical structures from simpler rules. So you have something like associativity coded in as an equivalent two-way rule. There's, for example, the introduction of something like a group operation in more symbolic rewrite systems. So just to introduce that this is another motivation of mine, the fact that there are mathematical structures that emerge from simpler rules. By the way, I think there's someone with an open mic. I'm getting some background noise. I don't know if you guys could mute your mics, unless you want to speak. That'll be helpful. Right. So one is kind of met with the question. These are the kinds of things that we work with at the institute. We have hypergraphs, which is what I would like to call symbolic vessels of discrete finite computable information. Right? They are very general objects, as you will see in a second, and they can encode a lot of different things in our research. And then we use these rewrite rules, which is how we get the things to sort of become alive, right, and to do work for us. So we are asking, how would you make these things operate like a calculus? So imagine that typically you can define a calculus on certain structures. Maybe when you are, I don't know, in primary school, you learn arithmetic, and you have a calculus of digits or a calculus of integers. And then as you progress, you might find a calculus of functions. You might find a calculus of groups in category theory or whatever. Things evolve. And so the question is, if you were to think of hypergraphs as your symbols, what would be a reasonable calculus for that? So hopefully by the end of today's talk, you will get an answer to this, or at least one answer to this question. And it's going to be motivated by kind of a more or less classical approach to graphs and networks, as you will see in a second. So let's start with that. So first of all, let's introduce hypergraphs. So we're going to focus on what are called simple connected ordered hypergraphs. So let me briefly say something about each of those terms. So simple means, okay, so before everything, a hypergraph is essentially a declaration of a bunch of nodes, which are some discrete elements, and a bunch of relations between them. And I say relations and not edges or lists or anything like that, because really the kind of structure that you impose on each relation can be of multiple kinds. So for example, you could have something like bags where there's no order of the elements. You could have something like lists, you could have something like cycles, or more sophisticated stuff. So we're going to be looking at ordered hypergraphs. That means that this expression of the hypergraph here on the screen, this list of lists, should be sufficient to characterize the hypergraph, right? So that means that the internal order of each of these lists matters. The total order of the lists, or the kind of order of the list of lists, doesn't matter, because this is just a collection of such things, but the internal order of the list does matter. And this is mostly to make contact with matrix algebra and tensor algebra, as you will see later. So that's what ordered means. Connected means that, as you can imagine, that there are no independent relations, meaning there's no disconnected components of the hypergraph. So everything can be connected by some sequence of adjacent edges. And then simple means that we are going to have only one relation occurring per site. Per site means that for a given collection of vertices in a given order, there will be only one edge. And also that vertices cannot be repeated on a single edge, right? So with those constraints, this is what hypergraphs look like typically. We have, a unary edge, which is just indicated as some kind of weight on a node. We have binary edges like these, for example, this directed edge over here. And then also we have ternary or quaternary and so on. And these are represented by, triangles and tetrahedra or higher polygons. So this is sort of the internal information. This is the rendering of the hypergraph in our Padlet currently. And this is the information that goes into that object, right? So if I make this actually visible, actually, I have it down here. So if I make the vertex labels visible, you will see that this is vertex 1, this is vertex 2, vertex 3, vertex 4, vertex 5, and this list over here just represents these edges, right? So the fact that we have an edge that just includes 1 itself appears as that little circle there. Similarly with 5 over here, then 2 and 4, well, we find 2 and 4, and indeed there is a directive edge between 2 and 4, and so on, right? So for example, in between 2, 3, and 1, we have 2, 3, and 1. So we have this filled triangle over here with the arrows in the periphery just to represent the internal order. Okay, so for all intents and purposes, these are hypergraphs in this talk. Just as a note, a generalization of this is that you can impose more general symmetry structures on the edges, meaning you could have something like an undirected edge that doesn't care about the ordering between, say, two vertices, or you could have cyclic edges where you only care about the cyclic ordering of the edge of the vertices, but not the exact sequential ordering of the edges, right? So okay, one classical connection that many of you might be familiar with from graphs is the connection between graphs and matrices. Well, something that should be noted is that hypergraphs generalize graphs in two different ways. They generalize graphs in the way that there are there are higher order edges, so the edges involve more than one vertex, or more than two vertices, and they do so in different ways. So you could have different types of edges also mixed in, right? The connection with matrix algebra happens as follows. So there is the function in our Padlet that is called Hypermatrix that extracts the hypermatrix object of the hypergraph. So you see that as an object here, you see that there's basically a collection of arrays that comes out of it. And what it does, with this little function to visualize it better, what it does is actually quite intuitive. So look at this hypergraph, which is the same that we had above. So what the hypermatrix of a hypergraph is essentially a sequence, or maybe formal sum, if you want, of ordinary arrays or tensors. I should always mention my obligatory comment about the name tensor. If I say tensor, I normally want to refer to a multilinear object with some kind of multilinear theory supporting it. So typically in, say, things like in general relativity or quantum mechanics, your tensors will have a notion of covariant, contravariant indices. So they will have not only a number of indices, but a type of indices. You'd have like 2 covariant, 3 contravariant, or things like that. These things are not tensors in that sense, right? These things are just arrays, which just have collections of indices which correspond to the vertices, and each entry of these objects is a scalar value that represents a weight in a way. In this case, because these are simple, they are just Boolean, so there's either no edge or edge between that collection of vertices. So let's understand what this information is showing, what these arrays are telling us. So these are graded by arity or order of the edge. So typically we will refer to the size of the edge as either size or order, with a slight danger of having a bit of a confusion with order in terms of the sequencing of the nodes inside. But we are the reason why I'm not willing to use arity, which is a very common term used for the size of an edge, the number of vertices involved in an edge, is that arity is typically used in algebra for operations, and we are going to talk about operations later on, and so I want to be careful with that. So looking at edges of size 1, so that's unary edges, we can see in the hypergraph that there's one over here on node 1 and there's one over here in node 5. So this, I mean, the nodes here actually have been sort of reshuffled a little bit in terms of the ordering of the numbers, but you can see that, you know, for this node 1 there's a 1, and for this node 5 there's a 1, and then the others have 0. So there's 0 and 2, there's 0 and 3, and there's 0 and 4, right? So let's check with the binary edges. So binary edges, for example, we have something between say 5 and 3, and we have something between 2 and 4. You can see that, you know, 5 and 3, let's see. So we have, yes, so nothing, we have nothing with 1, right? 1 doesn't have any pairwise connections to anything else, so we have this row with zeros, and then we have a connection between edges here, the 5 and the 3, and the 5 and the, what else? And the 5 and the 2 here. So there's this entries that appear, right? And we can just basically count the number of edges. You have 1, 2, 3, 4, and you have 1, 2, 3, 4 ones over here. So this is just the conventional adjacency matrix. Many of you will be familiar with adjacency matrices. This is exactly the adjacency matrix of the graph component of this hypergraph. But then, of course, when we go higher in the size of edges, then the array becomes larger, becomes thicker. There's more dimensions to this array, and so we have this cute little way of plotting the array, and we can actually just inspect where we have. So obviously there are, you can imagine, you know, 5 elements choose 3. There are many of them, and currently there's only 3 edges, right? You can see 1 here, 1 here, 1 here. So we can double check here with the array that let's find this. The edge here should be 2, 3, 1. So there's a 2, 3, 1 around here. There's a 1. Okay, so there is a 2, 3, 1. There it is. That 1 in the array is the element 2, 3, 1. So that's what it means. Let's find this one. This one is 3, 5, 1. So that's 3, 5, 1. Wait, what was that? Okay, let me see. 3, 5, 1. Oh yes, because things got reshuffled. Yeah. So anyway, so there's that one there that corresponds to this one, and then there's one more, if I can fetch it, which is over here. There's 5, 4, 2, which is over here. I think basically 2 and 3 are swapped in the reshuffling of in the sync convention. But you can see basically that what this does is it just represents the adjacency information of your hypergraph in a array structure. Okay. Any questions about arrays and adjacency information? Just as a summary, a hypermatrix is a formal sum or just sequence of arrays, each of them corresponding to a certain type of edge. In this case, because we are looking only at ordered edges, there's only arity or size that defines the kind of edge. But generally, you could have different symmetry types. You could have, for example, binary directed, binary undirected. You could have ternary cyclic, ternary ordered, ternary undirected, and so on, right? And so for each type of edge, you would have a array. So some kind of tensor looking object. And so we generically, this combination of different tensors, we call a hypermatrix. And of course, the motivation for the name hypermatrix is that we just play off the typical terminology for graphs. We say that a graph has an adjacency matrix, so a hypergraph has an adjacency hypermatrix, just to play with that terminology. Okay, so I take there are no questions or anything that you'd like to clarify at this point. So we're going to change subject slightly to talk about.
Actually, I had a question about the hypermatrix. Sorry.
Yeah, yes, go ahead, please.
So in this adjacency matrix, I'm still unable to understand the why there are ones at certain places. So are the ones to indicate that there are edges between that row and column? So for example, second row and fifth column, there's a 1. So that means node numbered by 2 and 5 are connected. Is that how I'm supposed to interpret it?
That's exactly how you should interpret it. Yes.
But then I think there are some ones missing here, right?
So the problem is that when the thing gets turned into a matrix, the indices are reshuffled for some reason from the names. So these indices don't go down in the order 1, 2, 3, 4, 5. I think they go down in the order. Well, you can see. I think 5 and 1 are the first two. It's not clear to me exactly how things are reshuffled because the indices are stored in an order that doesn't really care about the names of the vertices. So it cares about when they are listed in this sequence, right? So when you have this kind of sequence here, you find first 1, then 5, then 2, then 4, then 3. So that's probably the order that they are in here. But the point is, if you have a element in your hypergraph, element being a hyperedge, it will be represented in the right matrix of the according size. So as I said, if you have a binary edge here between 2 and 4, then in the 2, 4 entry of the matrix, you should have a 1. Otherwise, you get a 0, right? So more than actually trying to match the numbers with the entries, just check the quantities, right? So how many? So you have 2. I mean, forget about the exact positions of the indices because unfortunately this got reshuffled. I just noticed when presenting today instead of when I prepared it. So just notice that there's 2 unary edges here on 1 on the 5. So this first matrix gives you the vector, so to speak, gives you 2 1s and all 0s. Similarly, there are between 4 and 3, there's a binary 1. Between 4 and 2, there's a binary 1. Between 5 and 3, there's a binary 1. And between 3 and 2, there's a binary 1. So that's a total of 4 binary edges. So as you can see in the matrix, you have 4 1s, everything else 0s, right? And then if you look at this hypergraph, you will see 3 triangles, right? There's a 2, 3, 1 triangle, there's a 5, 2, 1 triangle, and there's a what is this one? 3, 4, 5 triangle. So in all this mess of zeros, you actually can fish out 1, 2, and 3 1s, right? Everything else is a 0.
Okay.
So those are exactly as you said, that's exactly how this hypermetrics works.
Okay, thank you. That really helps.
Okay, yeah. Hope that's clear. It's a very simple concept, but it's important to understand that one way when you represent a hypergraph, you really, in a mathematical sense, are representing a set of edges. But when you put it into a hypermatrix form, suddenly you actually have a sequential order. So that's a subtlety that is not very important most of the time, but when you actually are doing operations with these things, you really should take into account. So, these hypergraphs are kind of floating in space, and the only information that is encapsulated by them is the relations between the elements. But the moment that you want to represent them with a matrix, or if they are graphs or hypermatrices in general for hypergraphs, then you're going to have to set some fixed sequencing. And I mean, this is just unfortunate that the sequencing was not the same as the actual names, 1, 2, 3, 4, 5. But you can change the ordering in any way you like, as long as the relations stay the same. Things will be fine, right? Anyway, so that's the concept of an adjacency hypermatrix, and it's a way to motivate hypermatrices as objects if one is interested in studying hypergraphs for some reason. Now, what about rewriting? So rewriting is the main way that hypergraphs are manipulated in our systems, in the kind of research that we do at the Wolfram Institute. So I'm going to explain how rewriting works with a very classical example of graphs again. Same way that it's easy to understand adjacency matrices from graphs, and you generalize to hypermatrices by considering higher order extensions. We are going to look at rewriting rules from the very common example of the transitive closure or path composition kind of rule. So forget about this code here. This is just for kind of visualization purposes, and just look at this rule over here, right? So this rule this is what we call a rewrite rule. So the way you should be reading the left-hand side is as a matchmaking pattern, right? So you're making matches. You're basically pattern matching the shape of this hypergraph, in this case just the graph, and then you're saying, well, look at that context that is preserved between these two sides. So in this case, the context that is preserved is the three vertices, the vertices 1, 2, 3, and then make some change. In this case, the change is, as I said, this idea of transitive closure or path composition, right? So if you have an edge that goes from 1 to 2 and another edge that goes from 2 to 3, then compose them and basically delete those two and just write or add the shorter 1 to 3 path, right? And very importantly, note that these numbers here, these names, are just patterns, right? So it's not that you're going to go into a hypergraph and you're going to search for a vertex called 1 and a vertex called 2 and an edge between them. You're going to search for a vertex called whatever and a vertex called something else, and then you're going to search if there is an edge between them. And then together with that condition, you're going to search whether there is another edge connected to the second one into a different third one. And then if that's the case, what you're going to do is you're going to delete those two edges and you're going to create a new edge over here, right? So let's see this in action. So let's consider this particular graph, okay? It's, small directed graph with 5 edges, quite simple. And we're going to apply, so this little function, what it just does is it just applies it applies this rewrite rule. So the rewrite rule applies anywhere where it finds a match. So let me just make this a bit bigger, each of these. So let's look at the first. So what happened here was that basically the rewrite rule scans the entire graph and it finds the places where there is a match. So these are all the possible outputs of this rule application. So the first one, as you can see, there was something that changed between the vertices 3, 4, and 1. So these other vertices got left unchanged, but you can see that this 2 edges over here got composed into a single edge, right? So these were actually, I just wanted the one with labels because it's just easier to talk over this. Yeah, sorry. Yeah, this is much better. So I can speak to the number of names of the vertices, right? So you can see here, if you look at 3, 4, 1, that is a 2-edge path that connects 3 and 1. So the rule basically collapses those two and turns it into a single edge. So you can see 3 going to 1, just that's the edge. And so what the rule does is it says, okay, I found that's my first output, and then basically you can keep going. So what is another match? Well, you can see that there is a rule from 5 to, so there's a 2-length path from 5 to 2 via 1. So you delete the edge 5, 1 and you delete the edge 1, 2, and you get an edge 5, 2, right? So it's quite simple. You're basically, all you're doing is you're applying this pattern on the left-hand side, and you are updating that context that's specified by the pattern with whatever is in the right-hand side. So these are the 5 possible. I mean, just by visual inspection, it's quite easy to realize that there are 5 possible matches. So you can go either 3 to 1 via this length to path, 5 to 2 via this length to path, and then because there's a cycle in the middle, basically you can go in any of the 3 components of the cycle. You can go 4, 1, 2, or 1, 2, 4, or 2, 4, 1, right? And so these are these 3 matches, right? So over here we collapsed 4, 1, 2 into this directed edge, and here we collapsed 1, 2, 4 into that directed edge over here, and in here we collapsed 2, 4, 1 into this directed edge over here, right? So I think I said this the other round. I think this goes, it's here. It goes 2, 4, 1. Yeah, actually, no, I said it right. 2, 4, 1 into this edge here. So is it clear? I want to make sure everyone follow this because it's a very simple idea, but it's important that everyone gets it right. Do you understand how this rule applies to this graph and then gives you each of these 5 possible outputs? Anyone not sure how that happened? Okay, so something we can do is then once we have, let's say, once we have this first generation of outputs, right? Because the way these outputs were generated were, you look at the initial state, you apply the rule, and then you get an output. And then you go back to the initial state, you apply the rule in some other way, and you get an output, right? So this is the first generation of outputs. These are the first descendants of this state under the rule. But then, of course, what you can do is you can apply the rule again to each of the descendants, and so you will get more, because of course if you look at this state, which was the result of applying the rule once in this 3, 4, 1 context, you can see that there are several other contexts where you can apply the rule. I can still apply it to the context 1, 3, 4, 1 to 4. I can apply it to the context 5, 1, 2, and so on. So if we apply this 2 times, so this is the 2 generations, so it's the second generation of rules, we get all these many states, right? We get here again applied, here again applied. So there's a few more states that you get out of applying this thing twice, which just corresponds to applying the rule as many times as possible to each of these 5 initial outputs. And then finally, if we apply it 3 times, you see that we start to get something simpler. I mean, many copies of the same thing, but simpler, right? Like we basically get only 2 graphs. We get the graph that has 3 to 4 and 5 to 1 here, and then the one that has 3 to 1 and 5 to 4. And that's it, right? Like the others are just copies of this. This is just copies of that, and this is just a copy of that, and so on, right? So something that we can do, and then of course, after this, as it's visually obvious, all these states don't have a pattern that matches our left-hand side. Remember, our left-hand side was path of length 2, something that was, you can chain 2 edges. And there are chains of edges in all these intermediate states, but when we get to the end, all these things have no change of edges. They are just disjoint edges. So it means that when we apply the rule, we just get an empty list. We just basically say, hey, we are done. There's no more rule applications. So something that is very useful to do with in this kind of situation is to visualize what we call a multi-way system, which is really nothing but a acyclic directed graph that represents the evolution of these states. So in this graph over here, I'm just going to represent the graph in kind of sort of compact form, just for visual brevity. But we are omitting the directions and everything, just as a way to visually package all this information here of apply the rule once, apply the rule twice to the results, and so on. And we're going to identify the states that are the same. The states that are effectively the same graph, we'll just identify them. And so this first 5 are the kind of graphs, sort of named graphs that are different in the first generation, right? So remember that we have two that look like this, and then three that look like this, and so that's exactly what we're getting here, right? We have two that have this kind of shape, and then three that have this kind of shape, right? That's the first generation. But then in the second generation, it turns out that when you apply the rule to this output and this output, you actually get the same output out of the two. So there is some degree of confluence going on in this particular state over here, in this intermediate state. And then we saw that in the end there were two final states that were inert with respect to the rule, that the rule never applied to them, and there were just two different states. This one here that has 3 and 4 and 5 and 1, and this one here that has 3 and 1 and 5 and 4. Right? So those two things are represented at the bottom of this graph. So it's very important that you sort of visualize this as a more or less generic situation of rules, especially when rules are reductive, right? Which is our case, because we are reducing the number of edges, and so as you can imagine, if you take a graph, this rule will always make the graph smaller, right? Because if you have some number of edges, this is essentially going to reduce the edge count by 1 if it applies, right? So it's always going to be smaller, smaller, smaller. So eventually you're going to get to a point where either the graphs are empty or you have a graph where there are no more matches. So this is a typical behavior of a reductive rewrite rule, and it's very useful to represent this these kind of graphs to kind of map the causal structure of the process of rewriting. Okay, so let's do another example, but now with hypergraphs. So let's imagine that we have a pattern that looks like this, right? So let's understand this pattern a bit better. So what this is, and you can see the rule over here, which has the declared adjacency condition for matching, which basically means that you should have 4 elements and 3 cycles in each of the elements, right? So we have a 1, 2, 4, 1, 4, 3, and the 4, 2, 3. So basically, the fourth element is kind of cycling through the positions. First is in third position, second is in second position, and third is in first position. So the visualization of the rule is simply this. Now, note that the output of the hypergraph here is the single edge 1, 2, 3. So we are keeping the vertex 4 in that location simply as a visual aid. It's not part of the edge. We could have separated it or even deleted it for visual clarity, but just to make sure that we understand that the structure looks like 3 triangles that make up a bigger triangle. And what this rule is doing is basically saying, hey, collapse everything into a single triangle. So in a sense, this is a close analog of the path composition rule for ternary hypergraphs, right? This path composition rule over here is essentially telling you, hey, when you have edges that are oriented in this way, you can basically collapse and only keep track of the sort of endpoints of your shape. Well, similarly here, we have a situation that does look a lot like the previous rule, right? Because we have 3 triangles that have some internal structure that effectively matches, right? A kind of the directed structure of these triangles is sort of simplicial in a way. And so what you're saying is, hey, just collapse everything into a single triangle that way. So let's see what happens when we apply this rule to something like this, which has a few triangles. You can see, I mean, there's only ternary edges here, by the way. If you want to see the specification, I can just take the edge list of this, and you will see what it's made of, right? So it's just made of ternary edges, and remember, these are ordered edges. So the internal order of the vertices matters. And now we just apply the rule. So we apply it for a first generation, and you see that you get 2 different states, and then we actually run the same kind of system that we did here to visualize the the multi-way system, so this full causal network of possible rewrites, and what we get is this much smaller system. So we begin with a full hypergraph, then we apply on the left, then apply on the right, and these are two different states, but then both get rewritten to the same final thing, and it's this final hypergraph. And that hypergraph no longer, I mean, that only has two ternary edges, so there's no chance that a rule that requires a pattern matching with three ternary edges is going to apply. So that's the end of the rewriting process under that rule. So we can now actually visualize in much more detail with this multi-way system, which Nick has developed and is continuing to improve. We can see this much more detailed story of what's going on, because obviously there's a lot more detail in what's happening here than simply you have this state and you go to this other state. We get there in a very specific way. And so using this evolution causal graph option, we can actually visualize precisely what events happened. So you can see here that this event, the event that takes you from the initial state to this left-hand side state, it tells you that there is a rewrite event that happens exactly on this match, on the red highlighted sub hypergraph, and similarly on the right hypergraph here highlighted on this one. So you can see here the two events are sort of independent. They are basically parallel. There's no overlapping between them, and then both events give you basically a hypergraph that it has pretty much the same structure. This is effectively the same hypergraph under isomorphism. So, any questions about rewriting and how rewriting works?
I just asked in the chat if there was, but it's probably would not be a match, right? If you would be replacing 1, 2, 2, 3, like two edges by one edge, 1, 3, and the middle edge, the middle vertex would lie in another 3 vertex, then it would not like delete the 3 vertex, making it into 2 vertex. It would not be applied because it's just you have to specify all the structure around, right?
So, sorry, Pavel, I didn't hear the beginning of your question. There was some noise.
I wrote it in the chat. But it's probably clear. Probably it would not be a match, right? Applying.
Sorry. Oh, yeah. Sorry, I didn't see the chat here. Let me see. So let me read. I need to take this slow. So the rule 1, 2, 2, 3 goes to 1, 3. Would it be applied if 2 would lie in another 3? So is the question, I'm not sure I understand the question. Is the question if you had a ternary edge?
Yes. The 3 vertex, I mean 3 edge. If there would be a ternary edge containing 2, then this rule would not be applied.
Correct. Yes. That's a very good question. Yes, sorry. It took me a moment to understand exactly what you meant. So the question is, I think it's important to highlight for everyone here. So the question is, if you had this rule, which effectively, so the rule above, let me just, this rule here has the pattern 1, 2, 2, 3 goes to, so let me just write it here for concretion. Yep. Oops. So this rule effectively looks like that. I mean, the trans rule here, simply at the mere level of edges, it kind of looks like this, right? It looks like you have a list of lists, and this is sort of the shape of the rule. And I guess Pavel's question is, if I had something like this, would this 1, 2, for example, ever match this 1, 2, right? Is that your question?
Yeah, so no, if I was thinking, but I now see that in the picture on the right, you also specify like 2, you are not deleting any vertices. You kind of are not, all the vertices on the left has to be present on the right. And it cannot be kind of, it cannot happen that the rule kind of delete a vertex from another, which would normally be contained in another higher order edge or something like that, right?
I mean, you can. Oh, I see. So it's.
But,
I see.
But
I see.
I just noticed that there is two also in the picture on the right, so it's probably fine. So it's precisely what I was asking you. This would not be a match. This would not be a match, or it would actually be a match. It would actually no, actually it would be a match, but the two would remain there. The two would remain there, just would not be anymore part of these two edges. I see. Okay.
Right. So what's important to understand is that matches have a context, right? So basically the aggregate things that get mentioned both on the left-hand side and the right-hand side that are common to both, that's the context of the rule application, right? So if you are saying that you should be looking at vertices 1, 2, and 3, which are some generic names for pattern matching, and you delete the vertex 2 in your output, right? It is a question of, are you just considering the update of that edge? Sorry, the update of those edges independent of the vertices, or are you considering the vertices being updated as well, right? So the way that I am normally doing rewrites is that vertices are somehow dummy elements, right? They pop in and out of existence according to our whims for whatever we want to represent. Like the actual information is on the edges. So in a sense, if a vertex does not contain any, sorry, if a vertex is not contained in any edge, meaning that it's kind of floating over there, it might as well not exist, right? Because technically you can always add as many vertices as you like to any given hypergraph, and you add no information, right, to the data of the hypergraph. So the fact that vertices exist, get deleted or added, is only relevant if you're really hyper focusing on vertex count hypergraphs, right? So if you're really hyper focused on, hey, I really care about the number of vertices for this particular application, then they are effectively become part of your expressions, right? The actual individual vertices become part of your expression. Most of the time, the reason why I think it's a very good question is that most of the time in this work, the work I do, edges carry all the weight of the information, right? Vertices are basically just testimonial positions to represent the edges, right? And basically you just want them to be separate when they are separate. You want 1, 2, and 3 to be 3 different things, but you don't care what they are called. You don't care whether one is never used again or anything like that. They just, what carries the information are the edges. So for example, if you wanted to weight something on vertices, you would just put some kind of unary edge on top of them so that you have a sort of edge-centric way of processing them, right? Is that a bit better, Pavel? Is that a bit clearer? Sorry, Pavel, I don't think I heard you. I don't know if you said. We can't hear you. You're speaking. You were getting some choppy sound from you. Okay. Yeah, I see thumbs up. Always choppy, but everything seems to be fine. All right. So, any more questions about rewriting? There are some subtleties, as you saw. I mean, rewriting, should be said, is a very flexible paradigm, and therefore it's easy to get into, but you need to do some work to concretize and to make things kind of do the work for you. So the kind of rewriting that I'm using here is very focused on edges, very focused on basically the edge structure of a hypergraph, and vertices are mostly testimonial, sort of placeholder locus of memory where you just define your edges. So let's get into the center message of my presentation, which is a correspondence between algebra and rewriting. So I know that there are a lot of people here in this winter school that are knowledgeable about algebra. Hopefully you just got a bit of a sense of what rewriting does. And what I'm going to show you next, I hope, will show you that there is a very natural and direct connection between algebra and rewriting. Some of you might have heard of sort of string rewrite systems and their connection to monoids and to group theory and all that stuff. And that's indeed a classical line of work in this direction. But I think if you have this graph theory and adjacency matrix kind of experience and knowledge in your head, you can get a very quick connection between algebra and rewriting from what I'm about to say. So let's consider the following algorithm. Remember how when we apply the rewrite rule to the first state, right? Like we have this rewrite rule, we take our first state, our first hypergraph, and we basically just apply it once. So we find all the possible locations, we scan the hypergraph for all the possible locations that the rule applies, and then we take that, make the change, and sort of start over. So we go back to the initial state and do that over and over again. So one way to represent this is basically to just give a list of all the possible outputs. And this is what we did in this initial case. Now, another way to represent this is that instead of just listing all the possible outputs, what you can do is, because that's always going to be generally a set of hypergraphs or a list of hypergraphs, something else you can do is you can say, I'm going to represent the possible outputs in the same hypergraph. So I'm going to always have one single hypergraph as output. That hypergraph is going to somehow bookkeep all the possible outputs. So the way that we do this is something I call a one-pass rewriting, which basically means that a hypergraph is going to accumulate all the output information of the rules. So let's see how this works. So basically, the function one-pass rewriting using this rule applied to this initial state, which is the same as before, gives this output. So you might be wondering, what is that exactly? That looks like only a couple of things changed. So what this does is this applies the rule to a given matching. So for example, just like before, we have 3, 4, 1 as a location where the rule applies. And we know that what the rule would do is it would delete 3 and 4, and it would output 1, 3 as an edge. So what this algorithm does, what this function does, is it generates an empty hypergraph on the same set of vertices, right? And then it fills in all the possible outputs that start coming out. So when you do the first rewrite, you basically have vertices 1, 2, 3, 4, 5 as kind of floating there without any edge information. And you basically accumulate all the outputs of your rule applications. So this edge over here, the edge 3, 1, results from the application of the rule to the location 3, 4, 1, right? This edge over here, the edge 5, 2, results from the application of the rule to the location 5, 1, 2. And then this cycle in the middle, actually you realize it goes in the opposite direction, because these edges are the result of applying the rule to each of the 3 possible locations in the cycle, right? So the cycle, the edge 4, 2 results from the application of the path 4, 1, 2, and so on, right, for the cycle. So this graph over here just is constructed from the same vertices. So you basically take the initial graph, remove all the edges, and you have just an empty graph with the same names for vertices. And then what you do is you take the graph, the original graph, and then apply the rule in as many ways that you can, and you only look at the output of each rule application. So you forget about the entire graph, and you're only kind of accumulating sort of in a big bag, but you have some bookkeeping, meaning that you're keeping the names of the nodes where they are, and you're accumulating in that big bag every output of your rule application, right? So is it clear how this one pass function operates? did anyone not understand how this one pass rule function operates? It's basically, instead of just doing one rewrite at a time, what you do is you accumulate only the outputs in a single hypergraph. So in a way, you're losing information because the full information is to keep as many different threads of rewriting as there are pattern matchings, but instead it accumulates all the information on a single hypergraph, which has the advantage that then it's again a hypergraph of the same kind and it can be operated on similarly.
So the order of rule application will not matter? Is that a given?
Yes, it doesn't matter because it's only one. So that's why it's called one pass rewriting, right? Because it does one pass over all possible matchings, right? So again, I'll repeat with different words in case it makes more sense. So you take your hypergraph, this graph originally, right? And you say, where are all the places that the rule matches? But in the initial one, you don't apply one, it changes, then apply again, and it applies in different configurations or anything like that. You just take the first one, ask, where are all the possible matchings? Then you generate all the outputs for those matchings, and then you keep track of them in the same hypergraph, right? So remember how, the first time that we applied the rule here, this was the result. We started with this, we applied the rule in the 341 location, and we get this other hypergraph. So instead of doing this, what you do is you say, okay, that's a rule application, so I'm just going to keep the output. So I will keep 4, 3, and 5 as floating nodes, and I'll just draw one edge between 3 and 1. And then you will keep that as kind of your registry, and then you will go back to your initial hypergraph here. You will apply the rule again in a different location, and then that different location might be this one, 512, and so you apply it there, and you say, okay, I have a 5.2 output edge, so I'm going to add that 5.2 output edge to my registry hypergraph, which begins as an empty hypergraph on the same named vertices, and it gets as many outputs as there are rule applications, right? Is that clear how we get? So it might seem like a bit of a convoluted construction, but when you think about it, it is essentially what you normally do in arithmetic, right? When you're adding two numbers together, when you were in primary school just doing addition and things like that, you realize that you have a state which is your long number, the final answer of your addition, and you're basically adding several things, and you're kind of accumulating the things on the same objects, and you're carrying the unit to the next digit, and so on, and so eventually everything accumulates on a single site that has digits the same way as the other numbers, right? So this is similar. This is we begin with a single hypergraph and the rule, and what we do is we apply the rule. The rule can apply in many different locations, but what you're saying is I'm going to keep this one hypergraph as a registry, and it begins empty, which empty means no rule was applied, or no rules can apply, right? And then as you apply the rule, you keep adding the outputs to that empty hypergraph, right? And so this is what you get out in the end, right? If you start with this one, this is what you get out in the end. And this is an exhaustive process, right? You can just exhaustively go through for all finite hypergraphs and things like that, like we do computationally, you can exhaustively cover all possible pattern matchings, and therefore your hypergraph, this always terminates, and your output hypergraph always is some kind of hypergraph. If it's empty, it means that there were no rule matchings, and if it's not empty, it means that there will be some rule matchings. And if you have a clear count of your rule outputs, which in this case, for example, only have one edge, then you can basically do an edge count of that output hypergraph, and that tells you immediately the number of matchings that happened. So this output hypergraph naturally contains some information about the full range of rule application information. So again, the full range of rule application information is the causal graph that we wrote over here, right? So this kind of graph with all the matching in the edges is the full information of this rewrite system. However, if we want a bit fewer or smaller information, we can do something like this. We can accumulate output edges. So edge count means, or basically translates to number of matchings. And of course, every matching has an output that lives on the context where the matching happened. So you know that if you find an edge between some set of vertices, you know that a matching happened in that context. So it has that information as well, right? And of course, if we had several patterns that matched in the same context for some reason, then you would get several outputs, and therefore you could count the number of edges, because we are just focusing on simple hypergraphs for simplicity in this talk, but you could also count the multiple ways in which rules apply to the same context and so on, right? So anyway, is it clear how is it clear this idea, right? Like how you get from a hypergraph and the rule or set of rules. But one rule is fine, sufficient to illustrate this. You get one final hypergraph that basically catalogs or accumulates all the possible outputs. Any other questions to? Because this is a very simple idea, but it is subtle, and there are many things one could do, and we're wanting to do this one exactly. Okay, so some of you might be suspecting where this is going. I mean, some of you have seen this presentation from me before, but some of you who haven't probably are suspecting where this is going. So imagine that now, okay, so I begin with a hypergraph. I'm going to say hypergraph, but it's a graph in this case, just for simplicity. And then I do some operation with it, and then I get another graph of the same kind. And by this of the same kind, I mean it's on the same set of vertices and it has the same kind of edges, right? So let's say that we want to extract the adjacency matrix. So we just take the hypermatrix function and we, format it a little bit. All this code is just to format it nicely to represent it like this. And so this is the adjacency matrix of the resulting graph after this one pass rewriting. Okay, obviously that's what it is. Nothing special there. But note what happens if we take the adjacency matrix of the original hypergraph, right? Which I mean, call it B. We call A the resulting one. We call B the original one. And lo and behold, see what happens. If I do B squared, I get A exactly, right? So if you take the square of this matrix, it gives you this matrix. And you're like, okay, how is that? Is that magic? What just happened there? Well, this is the classic resulting graph theory that many of you have seen, that taking powers of the adjacency matrix corresponds to finding the number of paths of that length on the graph. So if you take the square of the adjacency matrix, what you are doing is you are counting the number of paths in your graph of length 2. So if you're doing the kth power, then you're looking for paths of length k in your graph. So this is a very classic resulting graph theory, nothing new. But what's very important here is that we have encapsulated this algebraic fact purely with a rewriting approach. Right? We just defined a very specific way of doing rewriting, which is I took some time to explain, hey, just keep this hypergraph, this empty hypergraph as a registry and start accumulating the output edges, and do this specific procedure with a rule and a hypergraph, and then it so happens that when you apply it to a graph, it's the same thing as doing the square of the adjacency matrix, and so that suddenly should kind of light up the bulb and say, hey, wait. So you're saying that in some kind of cases, for defining, when you define the rewriting specific way, it corresponds to doing matrix multiplication, right? And that's just exactly what happened. That this particular one-pass algorithm, when used with this rule, it corresponds exactly to matrix multiplication. So the lesson that I took a few years ago now, and that led to my collaboration with Xerxes and to eventually to come into the Wolfram Institute, and I mean that's why here I mean, that's basically why I joined and how I came to be part of this whole operation, is precisely the observation that, hey, I can basically forget about algebra. If algebra is proving difficult for some reason, I can just drop it and think of the rewriting processes that encapsulate the algebra. So I know that this kind of operation defines an associative algebra, because this operation defines matrix multiplication, which is an associative algebra. So the natural question would be, can I find other rewrite rules that implement other kinds of algebras, right? So that's kind of the bottom line of today's presentation. That sort of cements the correlation or the correspondence between hypergraphs and algebras. There's a very explicit one. It's one that doesn't require any kind of you don't have to do any extra work. I mean, once you define what you mean by rewriting and what objects you are rewriting, it's just a matter of setting up the function to do the work, or the algorithm, if you like, to do the work. And so you start to get algebras out of this. So I can report that we found several existing algebras in this way. A lot of things that mathematicians have looked at, and just to throw around some names in case mathematicians are familiar with them, we found dagger categories, we found operands, we found monoid actions, we found groups and monoids and semi-groups and all that kind of stuff. We've also found semi-heaps and heaps, which are this ternary, slightly exotic ternary algebras that have been documented, but they are much less known. So this idea really goes some length, right? It's not just a kind of an accident of graphs. It does go some length. And so, as I say here, one exciting prospect is that this is defined for any hypergraph, right? Any rewrite rule you can think of, and any class of hypergraphs, this is well defined. So it suddenly presents you with a landscape, or maybe rather a playground of possible algebras that are defined from just the rewrite rules, right? So one can basically play around with, say, hey, let's draw this little diagram that is my rewrite rule. What kind of algebra do I get out of this? So in order to systematize this, I would like to conclude my talk by presenting you this X diagram idea, which basically tries to make this connection a bit more systematic. So as we said here, we show that there's a correspondence between taking the square of an adjacency matrix of a graph and the length two paths in the graph. And this is well-known graph theory, nothing new there. It was neat to recover it in our rewriting setup, but it's otherwise known. However, let's go back to our example with this particular ternary rewrite rule, and let's apply it to this particular hypergraph. So when we do the one-pass rewriting, the result is quite obvious, because there was only two matchings and they were sort of independent. So the one-pass rewriting should just be the hypergraph that contains just the two outputs here. And so let's see. Well, what is the hypermatrix of that thing? Well, the hypermatrix of that thing is, I mean, as you saw earlier, is this kind of object, right? So this has six. This has six edges, so you can sort of fish out that there's a one over there, 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 there's one. So that should be 6 ones. I think there's 3 and those 3 over there. So you have 6 ternary edges, everything else 0. And so now we approach a similar problem. It's like, can we define a matrix algebra-like operation that will correspond to doing the one-pass rewriting with this particular rewrite rule, with this, 3 triangles kind of coalesce into a single triangle? Can we make that happen? And the answer is yes, we can make that happen. And the product is this. So this is called, I call it BM because in the literature, this particular array multiplication was first identified by Bhattacharya and Messner in 1990. So we now refer to this as the BMP, the Bhattacharya-Messner product. So I would regularly call it BMP because it's what we normally call it. So this formula, as you can see, has 3 objects ABC, which are 3 index arrays. and they get operated according to this particular pattern. So you go first index sum over the first array sum over the third index, second array sum over the second index, third array sum over the first index, right? So you see P is here, P is here, and P is here. So we implement this in Mathematica with this little function, and then we just do as before. We take the initial hypergraph, which is this one. We take its, now we call it adjacency cubics. We use the name cubics just to refer to cubic matrices, so it's 3 index arrays basically. And then the adjacency cubics is calculated with this function, and then we can verify happily that if we take the BM product, so we take that matrix over here, which is basically this matrix, right? We take this matrix, call this aijk. Each of the indices has an ij rejection, and we put it into the BM product. So this is BM, right? It's doing this particular multiplication, addition, combination. We just see that taking the cube in this case, right? We put the same matrix 3 times, so we do the cube instead of the square, as we did in the graph case. We get the correspondence there, right? We get that these 2 things are the same. So it is the same to do one pass rewriting and then compute the hypermatrix as it is to first compute the hypermatrix and then operate with a certain algebraic operation, which in this case is this BMP, this product defined over here, right? So this is really the kind of take-home message that I wanted to highlight today, that there is a very close connection between hypergraph rewriting and algebra in general. I mean, specifically hypermatrix algebra. And it's not only that you have a way to diagrammatically express that, which is what I will tell you in a couple of minutes as a conclusion of the talk, but it is a very mathematically concrete correspondence, right? You are saying that you can do 2 things invariantly in 2 different ways. If you are interested in computing the sort of cubics operation of this particular hypergraph, you could either first extract the adjacency cubics with the hypermatrix function and then do some algebra, or you could first apply some rewriting to the hypergraph and then extract the hypermatrix data with the function, right? So that is kind of the correspondence. This is what I called this section the this introduction here, the algebraic rewriting correspondence. This is what I mean by the algebra rewriting correspondence, that if you're interested in processing your hypergraphs in that specific way, you have a choice. You can either apply some rewriting algorithm to it and then extract the matrix information of it, or you first extract the matrix information and then you perform some algebra. And so in some sense, mathematically, algebra and rewriting are kind of interchangeable. And at least in the universe of hypergraphs, it is indistinguishable whether you're talking about rewriting or algebra. It's just kind of a point of view. It doesn't really, there is no way to tell that one is more fundamental than the other. There's essentially the same thing. It should be said, though, that algebra, in a sense, is more restrictive than rewriting. So restrictive is not necessarily negative. Restrictive means that it is much more constrained, and therefore working with it is much nicer. That's why mathematicians have worked with algebra for centuries, and rewriting is only kind of a marginal thing that is more a computer science era thing than a mainstream kind of mathematical practice. Although for sure some mathematicians have worked on rewriting, and so algebra has usually a lot more requirements to meet. So in particular, the kind of rewrite rules that correspond to algebra. So one natural question, by the way, would be in this context, one natural question is, all right, so you just said that those particular rules correspond to algebra. So this rule, the BMP, the kind of pattern thing with the three triangles coalescing into one, corresponds to the BMP product. And you also told us that this kind of transitive closure rule, this sort of path of length 2 composition rule, corresponds to matrix multiplications, right? Okay, fine. that's two examples, and maybe I mentioned more examples like operands and all those things. But the real question is, do all rewrite rules correspond to some algebra? And the immediate answer is no, because if your rules, for example, have many edges as input and many edges as output, they automatically don't correspond to traditional algebras. Because in order to have a well-defined operation, you need to have something that takes many things of the same kind and outputs a thing of the same kind, right? So if you tweak your patterns, you might end up in something that does not look like an algebra. So, meaning, for example, if you mix the sizes of your edges, if you have something that has a ternary edge and a binary edge, that is not going to be an algebra. It might be something like a module, it might be something like an action, but it might not be like an algebra. So it is a valid question to ask, do all the possible compositional mathematical structures correspond to something like a rewrite rule? My hunch is that probably yes, but the other way around, does every rule define a, give a well-defined compositional object? That might not be the case. So this is kind of where the research is at the moment, and this is one of the directions that we are working on at the Institute. It's a bit beyond this talk, because this talk is just about hypergraphs and hypermatrices, but this is kind of the more pure mathematical, more sort of abstract mathematics direction of the work. And so finally, as a conclusion, as I said, one way to systematize this correspondence is to say, actually, you know what? Because I know about this correspondence, why don't we use the hypergraph rules that equate this correspondence, or that execute this correspondence? Why don't we use those as the diagrams to represent the products? So what I mean by that is, sorry, Udi, yes, go ahead.
Are like adjacency matrices the only things that you have looked at algebraically? Are there other things that change in an algebraic way with rewriting?
Can you repeat the question? Can you expand a bit what you mean?
Sorry, there's a bit of background noise here. I was just saying that, are there any other objects that you have looked at other than adjacency matrices that change with rewriting? Algebraic objects.
Oh, I see. Well, not really, because most of the algebraic theory that has been developed for graphs has been developed for adjacency matrices, right? I mean, you could use the incidence matrix, you could use these other objects, and some other algebraic techniques are applied to those, but I am less familiar with those, and they are, in a sense, further away from the hypergraph proper, in a sense, right? Like the hypergraph information, and the hypergraph and the adjacency matrix are almost the same thing, right? Like they are, the only difference between the two is that the hypergraph typically doesn't have a natural order of vertices, and the hypermatrix does have a natural order of vertices. But that's pretty much the only difference between one and the other. But if you were to define other kinds of algebraic objects, like an incidence matrix, which is very common, or an adjacency matrix that has kind of condensed information, so things like accumulating all the higher order edges into pairwise edges and giving information like that way. That could be interesting. I haven't looked too much in that direction. Also because I think there is less developed algebraic theory for those, so there's less kind of grounds to build on. But yeah, do you have something specific in mind?
No, yeah, I mean, I agree that, I think that's a very valid point, that the adjacency matrix contains all the information, and a lot of the algebra has been developed for that. I was thinking somewhere along the lines of, let's say you have a simplicial complex and then you have some rewriting over there. Then I don't know, maybe like, so you can look at some rules that preserve the homology. That was the line of thinking I had for this question.
Oh, I see. Okay, no, but that's I see. So that's more on the direction of looking at your hypergraph as encoding some algebraic information more than representing the hypergraph with algebraic
Correct.
objects, right?
Correct.
Right. So in that sense, yes, in that sense, the kind of branding for the line of work that we do at the Institute is what we call infrageometry, where we're trying to think of the hypergraphs themselves as models for space, and therefore you can think about their topology, their homology, their kind of the typical analysis that you want to do for manifolds or for spaces, for topological spaces and things like that, that we do for hypergraphs. So yes, that's a different direction. The talk by Dugan tomorrow at this time, so at the same slot, will be on that topic. So that was very much timely for that. Thanks, Udi. Yeah, go ahead.
Yeah, thanks.
Next question, yes.
This might be a slightly different question, but what is the minimum information we need to say that two hypergraphs are the same? And I can also say why I'm asking this question later.
Well, maybe tell us why you're asking. Maybe I can specify my answer to your liking.
Okay, so thinking about it from an experimental point of view, like these hypergraphs represent either some qubits or qudits or whatever. And then through evolution, as the experiment progresses, they change. And in the end, we get an object that also, say, can be represented by a hypergraph. Then there might be some noise or something. In the end, if we repeat the experiment, we expect exactly the same hypergraphs. But due to noise in the system, there might be two different hypergraphs. So what is the minimum information I would need to say that my experiment went exactly the same and I have the exact two objects in the end?
Yeah. No, this is a fantastic. Yes, this is a fantastic question. Thanks for the question. I think it's very illustrative for everyone here. So the question that you're asking is basically what is called hypergraph isomorphism problem. And it is mathematically a very interesting question and very difficult question. But maybe in more concrete terms, this comes down to the encoding of your data, right? So if your experiment preparation, for example, only cares about, say, counts, right? The number of things that you see, then it's likely that you won't need to specify any labels for your hypergraphs, and your hypergraph will just be bunch of things, bunch of nodes, a bunch of edges, and that would be sufficient to characterize. So in that case, you can effectively use what mathematicians call an isomorphism of hypergraphs to identify when two hypergraphs are the same, which essentially just amount to saying, hey, can you see that first you check, like, are there the same number of vertices? Yes, then they can be the same. Are there the same number of edges? Yes, then they can be the same. So if any of these things you get an answer to no, then they can be the same. But if you only get yes, you only have the option open that they can be the same, right? And to prove that they are the same, it's hard work, right? Like you have to do several things. You have to, very inefficiently, maybe you want to list every single possibility, and you check that out of all those, they are the same possibility, and things like that. So in practice, most of the kind of parameters that one changes in applications are things like, do you care about your vertices having specific names or not? Do you care about your edges having specific names or not? Do you care about edges having different structure, like symmetry types? Do you care that they are ordered or unordered or cyclic or something else? Those are considerations to keep in mind when thinking about equality of hypergraphs, or what two hypergraphs represent similarly or equally. But beyond that, this is something that you will have to think about. If you're using rewrite rules, you will have to think about these kinds of questions, because when you specify a rewrite rule, you will have to define the pattern matching. So if, for example, we are using all these pattern matchings are unlabeled, right? Like so we don't really care about what things are called in any way, right? But I could actually label things, and you can actually put a label on these edges. I think I can actually draw show this functionality a little bit, maybe. So, oops, give me a moment. So I can, for example, select this and use the label and call this, edge 1. And I can call this, say, edge 2. Right? And so if I just return this, I have now a hypergraph that has names for edges. And when I actually look at all this mess, I mean, this is all just the colors and layout and so on, but you can actually see that the labels here, they specify that, this edge has this label and this edge has this label. So that's something that one can specify. You could also have vertex labels, and vertices themselves have names, right? So they typically use numbers just for simplicity, but they can be anything, and symbolic expression as well. So yeah, definitely that's something that one needs to keep in mind. I would say most of the time you care about whether vertices or edges have names, and whether counting is relevant. So if you care whether there are 2 or 3 edges, or just that there are some edges, that's another question. And then definitely the symmetry types. I didn't get into symmetry types just for briefness in this talk, but also if you want the edges to represent cyclic data or sequential data, or just set data and things like that. Does that answer your question a little bit?
Yeah. So just to reiterate, you mean start by asking the simple question, which is, are the numbers making sense? Are the number of vertices same? Number of unary, binary, etc. edges the same? And then
Right.
talk about symmetries and stuff. If the answers to all, at least one of them is no, then it's a no. But if they're all yes, then more
Yes.
work needs to be done by labeling these edges, right?
Yeah. Well, yes. I mean, there's, as I said, there are 2 components to this question. There's, on the one hand, the mathematical problem of hypergraph isomorphism, which is what you just described, where you can say, first count the number of vertices, then count the number of edges, then count the number of edges by type, by arity, by size, by all these things. If any of those things come out different, then you know that they are not isomorphic. But if they all come the same, you can't really tell. They could be isomorphic or non-isomorphic. And so solving the isomorphism problem, I mean, we have a function for that, but it is expensive. It takes some time. And then there's the other question that is not directly related to the mathematical problem of hypergraph isomorphism, but it's related to how you implement your experiments or your modeling, which is to do with what kind of information are you keeping track of? Like, what are your hypergraphs doing? So, for example, in my work, hypergraphs are typically diagrams, right? So they are typically mathematical diagrams. So for those, I usually have names for everything. Vertices have names, edges have names, and those names are like symbols in your mathematical equations, right? But in many other applications, hypergraphs are just like networks, and you just care that things are there. You don't care what they are called or that they should have a name, right? You just care that there are many things and they are connected in a certain way, and maybe they are modeling like a social network, or like a dendrite connectivity network in the brain or whatever, right? So it really is, as I said in the beginning, these objects are very flexible. They are very open-ended. They have a lot of expressive power, but that comes at a cost that the user has to do some work to get them to do what you want, right? So yeah.
Makes sense. Thank you.
Yeah, no problem. All right. So as a concluding remark, I just wanted to tell you that you can use this what we call plex diagrams, which is defined here in this function, to represent different products. So basically, this expression here is going to represent the indices of a formula. So what am I thinking of? Well, what I'm thinking of is that, if you have this formula over here, right? This is nothing to do with hypergraphs. to begin with, right? This is just a formula with arrays. But it does tell you that, this index should be contracted with that index, and it should be contracted with that index. So that's just a pattern, right? Like that pattern tells me that there is, one index, two index, then another index, and then there's the same index again, and then the same index again repeated over here, and then one other index, and so on. So this pattern over here, I can just, without caring about how you call the indices, I can just abstract. And the way I abstract it is by saying, I'm going to draw the pattern. And so this is, let me just copy this to show you here the analogy. So if oops, what happened? Let me copy the cell. So if I show you this formula side by side, you will see the analogy, right? So if I just copy the pattern, I just say, index 1 and 2, and then another that I call 4, then I and I, then there should be a 1 and a 1, right? And then 4, because it's the same as this one, and then K, which is a new name, so 3, and then P appears here, so that's 4, and then, J and K, those were named already, so that's 3, right? So I hope everyone agrees that this pattern here is just the index pattern that appears there. But note that there is a sum, there is a sum over this on the index P. So the index that I called 4, I have to specify as a summed index, and this is this other list specification, right? So when I process that, the Plex diagram gets rendered like this, and you suddenly realize, wait, I've seen that before. That's the diagram that we used for this correspondence, right? This is exactly the diagram that appeared on the left-hand side of the rule that made the algebra rewriting correspondence work for this particular product, right? This was the BM product that we applied here, BM on the left-hand side of this equality, and this diagram, this rewrite rule on the right-hand side of the equality. And then when we compute the Plex diagram, that's exactly what it does. It abstracts the diagram that makes the correspondence work, right? And so in turn, this becomes then a tool to represent these kinds of products. So we could just copy. Let me just so let me call this. What can I write? Okay, interesting. So I'm going to call these 3-4s because it just looks like the 3-4s from Zelda, and I'm going to see that the pattern should be 1 4 5 and then 4 and 2 and then 5 6 3. So basically there are 1 2 and 3 are in the same positions basically. So I and then so it should be I J K, which is in the right position, and then 5 J K, so that's going to be P Q, and then this is going to be Q. R, and this is going to be P R. Oops, P R. So just as an example, just as another example here, oh, apologies. And then I have to sum over P, Q, and R. So this particular formula, which is now looking quite different. I mean, you see that we are contracting, well, we are still contracting 3 QBCs, 3 cubic matrices, A, B, and C, but the pattern of contraction is quite different. Now it's, P contracts with P, R contracts with R, Q contracts with Q. And so that's basically the pattern that we get here. So the power of these plex diagrams is that instead of sort of fiddling around with indices, you can just specify the index contraction pattern, which is, again, list the indices like you would write them in the formula, and then list the ones that you want to contract over. And then this function just specifies the hypergraph diagram that would correspond to that product. So we can do that with the fish as well. This looks like a fish, so we call it a fish. And of course, this is the diagram of matrix multiplication, just something that looks like this with two pairwise edges. And then, of course, so if you're curious about how many can you define, we have this enumeration function, enumerate plex products, which basically allows you to oh yeah, I didn't mention what this means. So the nodes that are free indices are black. So the black dots, so you can just at a glance look at one of these diagrams, and you can know how many indices there are just by counting the black dots, and each black dot is a different index, right? So these enumeration functions are quite simple. They are just listing all the possibilities of ways that you can see. There's many of them, right? You have different shapes. So these are basically all the plex products, sorry, all the cubics products that have 3 cubices as arguments, right? And a cubics as an output. That's the thing. So these are proper products, right? Like ABC gives you another object of the same kind. So these are in principle all the options. There's a lot of them, right? They can be clearly classified by the shape that they are, the underlying shape of the product. But if I were to write them down, they would look like this thing. All of them look like this kind of formula, right? They all have this kind of shape or this shape, and it is a big mess. If I were to list all of these, it would look like a long list of just a bunch of indices being permuted. With this patterns, it becomes a little bit more transparent what's going on. There's still a lot of them, but it's much clearer that there's sort of chunks of similar products because they have the same shape, or they have the same structure of black vertices because they are always kind of in the periphery of the diagram or internal to the diagram, and so on, right? So this definitely helps a lot with doing some kind of taxonomy of these general products. So just to convince you that this is not just pretty pictures, oops, wait, oh yeah, it's here. There's this little function, plex product, that allows you to turn a plex diagram, which is just a hypergraph, basically, just a hypergraph with colored vertices. It turns into an operation that actually multiplies matrices. So here, A and B are defined down here. I have a bunch of like arrays generated here, like numerical arrays, for example. And this just shows you that doing the plex product with this diagram of these two matrices A and B is the same as actually doing their matrix multiplication in Mathematica. And so, for example, you can check things like this: the plex product of this diagram is associative, right? This is the formula for associativity, A, B, and then C, or B, C, and then A kind of thing. It gives you true here. You can check properties of these products. For example, the product that corresponds to this 3-triangle diagram does not commute. So if I permute Y and Z, I don't get the same. Then you can define some special arrays, which are basically arrays of 1s and 0s. If I run these things, yeah, I should probably do this just to make sure. So I'll just show you what these things look like, so you have an idea of what's going on. So these are, when I A is just a matrix, so I can just do matrix form of this. So it's just a matrix, and similarly with B, right? So that's just matrix multiplication. If I want to look at X, for example, I can do cubics form. And you see it's a cubics, right? It's similarly to A and B, but just the cubics. So that's the same with Y. And it's the same with Z. Like they are just cubices, different cubices. And so they get, this plex product, just, you specify a diagram and you put actual numerical arrays into it, and it operates them. And so these ones, for example, these are special QBCs. So this is a ones in the diagonal square, but otherwise zeros, right? So I have 1, 1, 1, 1, but zeros in the other positions. And so, for example, if I do by the way, they are RGB, so they are green, red, green, blue. So you see, there's the zeros over here, now the ones over here, and the blue one, it's like that, with the ones over here and the zeros over there. And if I do ID, this is just ones in the diagonal. So this is the generalization of the identity matrix, but as a cubics. And so for those special ones, you have this kind of identities, like the cube of an identity is an identity. If I put identities in the right places, I get back the same element. So that's why we call them identities, because they behave like an identity. So this has effectively implemented a calculus of hypergraphs, right? That was the original question, and that's pretty much what we've done, right? We've introduced a way to operate hypergraphs, and hypergraphs themselves specify products, and so we just now use those, and those define the calculus. So anyway, I hope you got something useful out of this, and I'm happy to answer some questions, but otherwise, thanks for your attention. Right, any questions, any comments?
So if
I have
not,
a question.
okay, go ahead.
So I asked this question in the chat. So is this connection between the rewriting rule and the algebraic operation, is it unique? Like, for example, can I find 2 rewriting rules that are doing the same operations?
So, not in a technical sense, meaning, strictly speaking, the answer is no, because the rewrite rules, when you say matrix multiplication, if you mean actual matrix multiplication, so the multiplication of matrices understood as 2 index arrays, then simply counting the number of hypergraph isomorphism classes, you know how many you have, and you know that there's only one graph of 2 edges, right? There's only this pattern, the rule pattern, right? Only this sort of left-hand side exists for that size of a graph, right? If you have 2 edges and you're imposing that you're simple, there's only that, and maybe another one, which is 1, 2, and 2, 1, because they are directed. But that's essentially the same, just with a 1 equals 3 vertex. So in terms of diagrams that correspond to operations, that is unique. Now, with operations that correspond to diagrams, that might be non-unique, just because of the reason that I mentioned, that have to do with sequentiality of vertices, or vertex labeling, basically, right? So the non uniqueness comes from the naming of vertices, comes from the sequentiality of vertices. The fact that hypergraph isomorphism classes basically mod out all the ambiguity from vertex relabeling, but matrix operations, strictly speaking, care about index sequentiality and index ordering. So in my view, you can, I mean, you get the same algebras, you get isomorphic algebras if you reshuffle your indices, right? Like as algebras, as in the mathematical sense, you get isomorphic algebras because they are technically different algebras because the sets are technically different because the kind of objects are different, but they are definitely in in bijection because they have the same number of elements, and the way they multiply respects that bijection because it is defined that way. So in a strict sense, the correspondence is unique up to that sort of index reordering isomorphism. However, it is a good question because the higher order rules, although they are technically different because they apply to different hypergraphs, to different hypermatrices, they can be effectively the same. And this I can illustrate. So where is when I define the rule for the first time here, right? I define the trans rule here. So imagine that instead of this rule, I define the following rule. So I'm going to define it for, let's say, hypergraph of 4 vertices. How am I going to define this? Yeah, 1, 2, 3, and 2. Wait, 1, 2, 3. Oh no, I need 5. I need 5 for what I wanted to show. No, sorry, I wanted 4. Yeah, so 1, 2, 3, 2, 3, 4, right? And the output is 1, 4. So imagine this particular rule. So in this rule, you have a ternary hypergraph pattern that goes into a binary hypergraph pattern. So, triangles are going into lines. And the way that this is a technically different rule, and the operation is not even an algebra. So the transformation is not even an operation in the algebraic sense because it maps ternary hypergraphs into binary hypergraphs or graphs. However, the underlying principle to this algebra, in my opinion, as far as I have seen, will be very, very analogous to this kind of situation. Because, as you can tell, it is almost the same, right? I just added some extra information to the edges here, but effectively what you're saying is I identify 1 as my kind of initial vertex and 4 as my sort of target vertex. And what I say is there is some connectivity structure between them. And what the rule does is it collapses all that intermediate structure to a single path between 1 and 4, between the source and target, right? So it turns out that when you write this out, the operations that you get are actually associative. So for example, even though the algebras are formally different in terms of sets, the kind of objects they operate, the algebraic properties are the same. So from a purely algebraic point of view, you can actually not distinguish between the bottom and the top rules here because they both define associative algebras. Different algebras, different size, different behaviors and other characteristics, other algebraic characteristics are different. But from the point of view of just the classification of algebras, they are the same kind of algebra. So there is a degree of, although the things are technically unique, and they are, different diagrams produce different algebras, and these are technically separate. There's big collections of rules that all implement the same kinds of algebras. Another quite noteworthy example, I'm going to try to actually illustrate it in a different notebook. And I don't know if I have it here actually. Yes, unfortunately I don't have it here, but I can write it very quickly. So basically, in semi-heaps, one typically uses the fish diagram. Actually, I need to find the fish diagram. So yeah, so this diagram, right? This thing, it is usually, let me just bring it to the rules. Yeah, here we go. So I don't need to specify this. And I have a list here. Oh, these are bad names. These are bad. Oops. Sorry, I just need to. ERP. Yeah. So if I produce this rule and the output is AB, oh, I have to clear C as well. If I, and this produces just A, B, C. Let's see if this works. Oops. Yeah, that makes more sense. So it's a little bit distorted. Oh, because something is duplicate. Oh yeah, this is just one too many. Oh yeah, that's much better. So this is the fish rule, and actually the reason we want this is that A B C D, no, A B C P Q R. Yeah, that's much better. So you see here on the left-hand side, you have a fish pattern between A, B, C, and there's kind of an internal fish to the ABC location. And then the thing gets rewritten to sort of collapse the fish into a single triangle. So it is a big mess of letters over there, but I think diagrammatically it's quite clear what's going on, right? So it turns out that algebraically, this thing gives you a ternary algebra, ternary because there's three triangles in the diagram, right? That satisfies the following axiom. So if you take three arguments, they would look like x, y, then whatever, a, b, whatever, yeah, a, b, c, and that will be equal to, because it doesn't like this, that will be equal to x, and then you flip y and b, so it's b, a, y, and then close that, and then c. So it's this kind of, I don't know, it's this kind of equality. So that is the algebra that you get out of this diagram. And the reason I'm saying this is that you actually get this exact same algebra if you use instead this diagram, which now I'm going to copy from this one. It's much easier. So it not only is different looking in terms of the contraction, in terms of the actual vertex structure, but it is defined on graphs instead of hypergraphs. So what do I want? 1, 2, 3, 2, and 3, 4. Is that right? No, this goes to 1, 1, 4. Yeah. So this is the pattern over here. This is a non-circulating path, right? Like it goes, I call it a zigzag pattern. So you go 1, 2, and then 3, 2, and then 3, 4, right? So you have some kind of, two edges swimming in one direction and one edge swimming in the opposite direction, and that composes to kind of like the net flow. So you have two things flowing backward, two things flowing forwards, and one thing flowing backwards. So you get one thing flowing forward, kind of thing. Just as a way to picture what this rule is. So if you impose this rule, you end up with an algebra that is exactly the same. It has exactly this axiom, this kind of behavior. It's ternary because there are 3 edges on the left-hand side. That's what the arity of the operation corresponds to. But when you operate it and you find how it behaves, you find out that it behaves with this axiom exactly, just like the fish. So it turns out that the fish and this particular pattern, the zigzag, I call it, they both represent the same kind of algebras. So they are technically different algebras, and so technically the rule uniquely identifies them because they are defined on different sets. They have different cardinalities. They have different properties, but under some criteria, like the algebraic classification, the algebraic species, so to speak, they are indistinguishable. So under this sort of, if the question is what are the algebraic species, fish and zigzag are the same species in that sense, right? So I hope that gave you some extra context in your to your question.
Any further questions? If not, then we are right on time. Let's thank Carlos. Thank you for the wonderful talk. And sure, take the discussion on Discord. I think there'll be some material that Carlos may share and make available on some of the channels. Feel free to continue the discussion. Some of these things may also be involved in a few projects that you people are doing. So let's then spend the rest of the afternoon for student mentor discussions before we meet again at 3 p.m. for Nick's talk. Just note one thing: at 1 p.m. mentors will be in a separate mentor meeting. So some of us may not be available from 1 to 2, but before and after we are around. Thank you, everyone, and see you soon.
See you, everyone.
You.